our colleague Olof Mogren from RISE. And I should mention that Olof has a bit of a special place in Climes because he will be actively contributing as a member of the core team of the center. So Olof, please.
Thank you. Right, so my name is Olof. I'm a research director at RISE, colleague to Joachim, who gave this introduction just a minute ago. My team and we work on foundational AI research and applied AI research, where we apply it to sort of problems relating to the Earth, climate change adaptation, and managing climate events. I'll go through some of the work that we do, but first I will just have a couple of notes on the current ongoing climate crisis, which is driven to a large extent by climate change. We're currently in the middle of the 6th major extinction event of the history of the Earth, and as I said, climate change is a driving factor. Other effects from humanity, of course, is playing a role here. According to the UN and IPCC, climate change has altered ecosystems, marine ecosystems, terrestrial freshwater ecosystems already. And for example, the coral reefs have already declined to about half of what they were 150 years ago. By 1.5 degrees global warming, we expect a decrease of 70 to 90% of the coral reefs. And by 2 degrees of global warming, we expect about 99% to die. Mammals and terrestrial animals and terrestrial life face a similar change as their habitats are changed, and animals are sort of required to move to new places or just disappear. So biodiversity is also part of the solution here. It can also be a way to improve or fight climate change. Restoration can help the natural carbon sinks, and it can be a strategy to quantify biodiversity with AI-based techniques to be part of decision systems. When we are doing this, which we are working on, is to use these kind of devices. This is a passive acoustic monitoring device that ecologists put up in the forest to collect sounds from the environment. Coupled with AI-based analysis, this can be a powerful biodiversity monitoring tool. And so this is one work that we've been working on. It's called few-shot learning. It means that we take a large base training data set and train our machine learning models on this, and then we require only 5 examples of our target class. And this is currently something that we're discussing with ecologists on how to put this into real use. So this data hungriness of current machine learning models is, of course, one problem that we can address with such solutions as few-shot learning. Another approach that we're also looking at is active learning. Active learning is when the computer trains using a data set, and then it can also ask an expert for annotations where it's really needed. But those annotations are typically expensive, especially in these kind of applications where you need ecologists and naturalists that are experts in their fields. So you don't want to do this too much. We've taken this technique and moved it to a situation where we want the labels from the ecologists to be strong labels instead of weak labels. Weak labels are quick to make. Strong labels are more difficult to make. In this case, we're looking at sound event detection. That means that we need a start point and an end point, an onset and an offset. And the specialists need to put this quite detailed. But with our technology, the machine learning model, while it trains, can give hints on where events may start and may end, and that can help the annotation process. Right. So wetlands are a major carbon sink. Wetlands cover about 3% of the Earth's area, but it's storing twice as much carbon as the forests on the Earth. This makes them very important, of course, important thing to study, and important also in the mitigation attempts that we have. So for this, we are looking at Earth observation, which is taking data from satellite imagery coupled with image analysis, which is AI powered, and this I will just mention sort of what we are doing in that direction. So one thing that we have done is this wetland mapping project together with the Swedish Environment Protection Agency. They inspect wetlands in protected areas, and we can use this to train our model, which then can generalize to other areas over the whole landscape. And then we can generate this map, and then you can sort of find out where we have wetlands that could be worth saving and also restoring. Another thing we do with Earth observation is stream flow forecasting. That's a tongue twister. We have done this with satellite data, which we couple with historical readings of temperature and downpour. And this has been done thus far on Swedish data from, for example, this Kryckland catchment area, where we have collected data for several years. We've trained this model on this, and we've made dense predictions. So we predict in every point in a map, and we can make a map of the actual flows that are flowing in the area. We're currently talking to researchers in Sao Paulo to sort of generalize this to Brazil. The third thing on Earth observation is land cover classification. This is a task of segmenting a map and building a map of the different kinds of land covers that you have. You have the urban areas, you have the forest, you have the agricultural areas. And this is important to track to be able to see how human factors are affecting the environment. Here we have went a little bit sort of more foundational on the computer science part and looked at what are the state-of-the-art models doing. To the left, you see the original image on the top row. In the middle column, you see a grayscale version of this image. And to the right, you see an image where individual pixels have been swapped within one region. And when you swap these pixels, the model is dumbfounded. It doesn't work at all. But removing the color information actually doesn't make that big a difference. This is perhaps not so surprising, but it's further more severe when you do this pixel swap. Here, by different fractions from the left to the right, you increase the pixel swapping on the middle row here. And on the bottom row, we also remove information about the context. So while you have the context, that may sometimes be enough for the model to make clear predictions of the actual target, which is here highlighted in yellow. Right, so those were some examples of what we do. What can be done with AI? Well, what cannot be done with AI these days? We can do many important things. We can do predictions of extreme events, flooding, drought, wildfires, landslides. People are working on this. We can also make important optimization systems, transportation systems, energy systems, heating and cooling. We can work on planning of green infrastructure. So, for example, as was mentioned earlier, with the planting of trees, see all the aspects of what happens when we start planting trees to make a carbon sink. Will we increase the risk of a wildfire, for example? Also scenario estimation, visualization, and different kinds of data analysis. So with this said, I will thank you all for listening. And I don't know if we have time for a question or if we...
Well, first of all, thank you, Olof. And then I do think we have time for one question. Do these things work with that?
Yes, they should.
Okay, so if anyone has a question, they will get this nice cube microphone and can ask it. Any courageous soul?
Everything is clear.
Yeah,
that's great.
If not, perhaps just a question. So obviously you highlighted both monitoring and forecasting, and those are two very different things. So I assume that also the algorithms that do these sort of things are very different and need very different types of data to be trained.
Absolutely, they need different care when doing them. Typically, the forecasting is done with some sort of a time series data, and the monitoring or estimation is typically done with data where you have sort of this is now.
Excellent.